Okay, so we just worked through A, our number 12 of the gas laws.
Sorry about that.
Sorry, Colin. But you can pause this and look through it. Go left to right is how we did it. If you have questions, let me know. On B, we're going to calculate the mole fraction of H2. So all we have to do is take the moles of H2, which is 2.50 moles, and we divide it by the total moles, 3.499. That's it. So what do we get? Okay, and there's no unit on that because the moles will cancel. All right, so then we need to calculate the density in grams per liter of the mixture in the flask. So this is where you would take N, and remember N is grams per mole, right? And you're going to plug it into PV equals nRT. So we're going to change that N to grams divided by mole RT. Okay, and I'm doing it like I would on the AP exam because I won't have these other things memorized, right? I want to get it in grams divided by liters. Well, volume is my liters, so I want to get volume on the other side. So I'm going to go grams divided by volume equals pressure times mole divided by RT. Did I rearrange that correctly? Okay, and then we just take what we had up above. Remember, the mole is the mole total. And we plug in. So we have our pressure total right here. So we're going to put our pressure total in. So 14.0 times total mole, 3.499, divided by R, 0.0821, times by temperature, 400 K. You got a really ugly number, okay? 1.49. Okay, and it would be grams per liter. So don't forget your units. It is. Yeah, I use the cursive L just because capital L sometimes gets messed up with something else. Okay, so the mixture in the flask is ignited by a spark, and a reaction represented below occurs until one of the reactants is entirely consumed. Give the mole fraction of all species present in the flask at the end of the reaction. So if we look up here, I'm going to bring down real quickly what this is. 2.5, right? 0 moles of this, and 0.500 moles of this, right? That's what it starts with initially. Okay, it's a 2-to-1 ratio. What am I going to run out of? The oxygen. So if I double the oxygen right here, I only need 1 mole of this, right? To use up the 0.5 moles of that. I'll be okay with that. So at the end, how many moles of this have I made? 1 mole of this is what is made. How much of this do I have left? None. And it's a good thing to show visually what's going on here. How much of this do I have left? 1.5. So I have 1.50 and 1. It wants me to give the mole fraction of all species present. Well, what's the total number of moles? 2.5, right? Okay, so that's the total number of moles. So to get the mole fraction of H2, I'm going to take 1.5 divided by the 2.5. It doesn't tell me anything about the argon. Let's see. Of all species in the flask, yes, argon is still there. So Oops, let's erase this. It's actually even, so we've got argon, I got to put it back in, 0.449. It doesn't react. So basically it's 499. Basically 0.5, right? Because we have 2 sig figs there after the decimal. Okay, so you're right, it should be 3, right? 3 overall. So H2, how do we have plus 0.5 plus 0.5? No, this is what's left over right now. It doesn't say to start with, it wants it at the end of the reaction. Right? Okay, at the end of the reaction. So we're going to go here, this will be 1.5 divided by 3, so 0.5. And then oxygen will be 0, right? Water will be what? 1 over 3, which is 0.33 repeating, so 0.34. And argon is 0.5 over 3, which is 1/6, which is 0.16 repeating, so 167. And we'd be done. Now you do need to show the fraction and then give the decimal when they ask you for mole fraction, so I know what you're doing. And you probably could say total moles. That would also be a good thing to show them that you know how to do that. Oh yes, it would be rounded down. So 0.33, thank you. Okay. Did you follow that through? Everybody okay? Any other questions with that? So they like to use PervNert. They really like to use PervNert. Okay? All right, so if we're done with that, what I'd like to do is go on to this. So if you've got, this is something I gave you at the beginning with all the science practices, big ideas. This is what we've covered so far. So this is what you'll be responsible for the semester test. So in the science practices, practice 1, 2, whoops, come on. This should have been one of the things I gave you and you get put in your techniques or your notes, one of the two. Yep, all the objectives, the 6 big ideas and all that fun stuff. Yep, I told you to go through and highlight what you... Okay, so these are things that you're supposed to have, we've already done in lab, we're probably going to do again in lab. There's some that we haven't done, 2 and 3 here, and 3, 4, and 5 here. We will get to those. Basically, it's just learning to, remember how I told you at the very beginning, you're going to need to learn how to write a lab notebook, and you're going to get better, hopefully, as things go on. I'm not going to start, I'm really start next term, I'm really going to be pushing you to do better. Make sure you write your procedure down, make sure you write your purpose down, make sure you, whatever I haven't given you, make sure you write down really well. Be able to relate knowledge across different scales and concepts and representations. So if you're able to, remember when we did the PES, be able to look at that PES mark, the little peaks, and be able to say, oh yeah, that's 1s2, 2s2, 2, be able to interpret, that's what that is. Okay, going up, maybe. Okay, these are the 10 mandatory labs. We've done 4. Okay, we're going to be doing more coming up. A lot of the ones coming up.
You highlighted everything except for
2, 3, 1, 2, and 3, 4, 5. Okay, these are things you should know, so that's why I put a dot by them. And then you can go back with a different color and sort of highlight with a different color what you need to work on. Need help. Okay, well, I can give you a yellow. Okay, going down here. So we have done 16, 19, 2.1, 2.22, and we'll be getting into the others. Okay? There are a lot of them with titrations, a lot with heat, and then Le Chatelier. So they're not hard ones, but we do have to make sure you know all of them because they can be accessed or referred to in the AP test. Okay, so big idea one, you'll notice that I went down from highlighting the whole thing just to highlighting the little parts. So big idea one basically is about the chemical elements, are fundamental building materials of matter, and all matter can be understood in terms of these arrangements of atoms. These atoms retain their identity in their chemical reactions. This has to do with everything that we've done that has to do with elements. Their Lewis dot, their electron configuration, their families, their way that we put them together into chemical formulas, the way that we can change from grams to moles to molecules, all that is included in here. So as you go down, and it sort of breaks it down, this is a big idea. Underneath that's enduring understandings. Underneath enduring understandings are essential knowledge. Underneath essential knowledge are learning objectives. So the learning objectives to me are the ones that make more sense. So justify the observation that a ratio of masses of constituent elements in any pure substance of that compound is always identical. In other words, H2O is always 18.015. Has 2 hydrogens, 1 oxygen. That's what they're saying. Okay? So we've done that kind of thing, going down a little bit farther. So everything on that page, everything on the next page. Okay? And we're going to go through all these, explain the distribution of an atom based on data. That would be like PES. Analyze data relating to electron energies for patterns and relationships. You know, which ones are more energy to give off, which ones have less. That would be our light. So we're talking about our lights. Describe the electron structure, 1s2, 2s2, or using quantum mechanics. This also is the Coulomb's law that I had you guys do that packet on, that POGL packet. Describe the electron structure using PES or ionization energy. Remember, ionization energy is how much energy it takes to take an electron off an atom, or Coulomb's law to do. That's quantum numbers. Those are quantum numbers. Okay. Those aren't officially on, but you do need to be able to recognize them. They're more leaning towards the PES and the electron configurations. So make sure you know those. Explain the distribution of the electrons using Coulomb's law to analyze and measure energies. Predict and or justify trends in atomic properties. So we went through all that. In fact, Corey, you have stuff that you're going to share on your families that you did. So he needs to have an email address or something that he can send you stuff with, because he did mega amounts of research on each family. So he had, I know you had iron through zinc families. And he did a half a page for every element. And so rather than kill his printer, I'm just going to have him send it to you electronically so you have it.
I think I could do that. I totally would. I would make an entire PowerPoint presentation.
I made like a PowerPoint presentation that has more information than the actual paper that I have.
We probably should have done that.
Yeah, if you
I
give me
told you
more,
that, but you told me to print it out.
Okay, I'm sorry.
if I known I had like enough time to do that, I would have done that PowerPoint and the whole thing with the document to go with it that you would read as you went through the PowerPoint.
Whoa,
Absolutely, I love doing stuff like that.
you love doing stuff like that.
PowerPoints with. I know PowerPoints are nice, but it was.
Okay, let's focus again. Let's come in and focus. Okay, so predict and justify trends in atomic properties. So we need that stuff. What's happening with that? Justify the arrangement on the periodic table. Why is it put where it is? Why is it in the part of the family? We talked about that already. Analyze data based on periodicity and properties of binary compounds. You could be forced to identify an alien element. Where would it fit? What families would it fit in according to its things? Explain why a given set of data suggests or does not suggest the need to refine the atomic model. So remember, we had several different models. We had Bohr's, we had J.J. Thomson's, we had Rutherford's model, we had Dalton's model, we had the quantum mechanical model. And all of those have good things, but they also don't all encompass everything that is in an atom. No one model is perfect. Okay, the quantum mechanical is probably the best we've got right now, but it's still not perfect. Okay. Dalton's, yeah, it was probably a lot simpler, but it didn't explain stuff. Okay, given information about a particular model of the atom, students determine if it is consistent with the data that you have. Using data from the mass spec, remember that lab? Okay, figure out what is going on there. Remember, mass spec told me different what? Does anybody remember? Concentrations of isotopes. Okay, justify the selection using spectroscopy. That's the light. So remember when we were looking through the light and you were able to see where the bright line spectra was? Be able to justify and figure out what we have by that. Okay, going up again. Next page. Design or interpret the results of an experiment regarding the absorption of light. So that would be, here is the spectrum for hydrogen and helium and oxygen, and here's a spectrum from an unknown planet, what things are in that unknown planet. Express the law of conservation of mass, qualitative and quantitative, using symbolic representations and particulate drawings. So in other words, here's how many oxygens I have, draw that. This is how many hydrogens I have, draw that. Here's how many waters I can make and what's left over.
You know what kind of test is the hardest?
What?
Multiple choice.
Multiple choice, huh? Okay.
Oh, absolutely.
All right, apply conservation of atoms to the arrangement of atoms in different processes. Again, be able to visualize and draw that for them. The gravimetric, that's the one that we took and we plated, or we took a sample and we were trying to find the concentration. Remember, we use the vacuum filtration tubes. Remember that? Well, not the colorimeter. Where we did it very first, where we had to heat it up with the crucible, and then we added water, and then we added the copper wire, and then we got the silver out there. Remember all that? That's gravimetric analysis. That's been on there a lot. Okay, that's with a lab. So you need to be able to analyze and figure out, using empirical formulas, the ratios, design or interpret data from that. And then we get to big idea 2. And this is chemical and physical properties of materials can be explained by the structure and arrangement of atoms, ions, molecules, and the forces between them. So this is the stuff that we need to do with hydrogen bonding and things like that. So as we come up here to this other side, predict the properties of a substance based on their chemical formula. Are they polar? Are they nonpolar? Explain how they their properties based on particulate view. Do they have a polar side, a nonpolar side? Are they going to hydrogen bond? Are they going to have a dipole-dipole? Are they going to have LDFs? What kind of bonding do they have? Okay. Explain the relative strengths of acids. We didn't get to yet. We're not into acids, so I did not highlight this one. Okay, so learning objective 2.2 we have not got to yet. 2.3, using aspects of particulate models. In other words, particle spacing, motion, forces of attraction, to reason about observed differences between solid and liquid phases and among solid and liquid materials. Use KMT, this is what I've been talking about, the Toddler rules, right? Kinetic molecular theory, that's Toddler rules, okay? And concepts of IMF, those are the hydrogen bonding, the dipole-dipole, and London dispersion forces, okay? To talk about the properties of gases, both macroscopic, both ideal and non-ideal. Remember, ideal is toddlers, non-ideal is teenagers. Get real gases, teenagers, right? So I gave you some cues on how to remember that kind of stuff. Use the aspects of the particle motion and spacing to reason about solids and liquids. We basically have talked about that already. Some of it seems to me like a bunch of repeat. Okay, intermolecular forces, IMFs. We did chromatography. Remember that had to be pulled apart according to the polarity of it. to draw and interpret representations to show interactions. So if I've got a water molecule and a water molecule, I've got to be able to identify it so that that O is attracted to an H, not an O attracted to an O, because that would be a repel. Create or interpret representations that link the concept of molarity with particle views of solutions. So if I have a large molarity, I'm going to have lots of little particles in there. If I have a low molarity, not so many. Be able to, this is important, be able to design an experiment where you could separate using paper chromatography. We did that with the principle, with the principle, remember that? Or a column or distillation, so we could have evaporated off. Then we come down here, explain the trends in properties and predict property samples with particulates and permanent dipoles based on LDFs. Then we go down a little bit farther, qualitatively analyze data regarding real gases to identify deviations from ideal gases. And we talked about those. Does anybody remember what the deviations were for real gases? I take up space. I attract and repel. Get real. There aren't elastic collisions. Okay, so those things are going to affect how my data is. So if I take up space, I can't say it has zero volume. If I'm attracted or repelled, if it's not an inert gas, it's going to have problems there. And if I have collisions going on, we've got issues there. So describe the relationship between structures of polar and the force of attraction between molecules. Apply Coulomb's law. If you don't know Coulomb's law, you need to really go back and look at that. Describe interactions. Explain observations about solubility. Remember those solubility rules? NAG-SAG. Remember NAG-SAG? Okay. We need to make sure we understand those and what's going on there. Polar dissolves polar. Do not ever say like dissolves like. Okay, they will give you nothing for that on the AP exam.
Wait, what?
They will give you nothing for like dissolves like, but if you say polar substances dissolve polar substances, they will give you that. So you need to be more descriptive. Explain the properties, phases, what happens, vapor pressure, viscosity of large molecules compared to small molecules. Remember, that's more Graham's law. Small molecules are going to move faster than large molecules. It's like Fat Albert trying to run around the track compared to a little skinny thing. Okay, they don't have as much mass to move. Okay, predict the type of bonding represented between, so you need to be able to know how to identify that we did this lab. Remember, ionic, covalent, polar covalent, metallic, or network covalent. Rank and justify the ranking of bonds based on polarity, based on the locations of the bonded atoms in the periodic table. Okay, so remember, far apart on the periodic table, you're going to be ionic. The closer you get, polar covalent. If they're really close and they're both non-metals, you're going to be covalent or molecular. And if you are both in the metals, you're going to be metallic. Okay. You need to be familiar that SiO2, which is sand, is a network covalent. Diamond is network covalent. Graphite is network covalent. Okay, silicon often does network covalent. Create visual representations of ionic bonds. We did that where we actually took the electron off and put it on the other side, made one positive, one made one negative. They have outside shells the same.
Okay, now breathe.
Going on, explain how bonding models involve delocalized electrons. So basically show what a metal bonding is or metallic bonding is by showing those electrons being mobile. Using Lewis dot and Vesper, predict geometry. We've done this. Identify hybridization. Remember SP, SP2, SP3, SP3D. Design and evaluate or collect data, and it just keeps going and going. The song that never ends. So we're going through all of this. I'm not going to keep reading this because my voice is going and going. But sort of look at this as we're going, and hopefully you're highlighting this. If you have any questions, we can go over that. Metal alloys. Remember, metal alloys are metallic bonds. We made brass. Sea of electrons is they also call it delocalized electrons because they can move around. Explain the representation going on, create and represent covalent bonds. How do covalent bonds work? Remember, they're sharing bonds. So they are going to be shown in a Lewis structure as sharing, not ripping off, and there won't be a positive and negative side. Okay, big idea 3. Changes in matter involved rearranging or reorganizing the atom and transferring of electrons. So this is where we worked with electrochemistry, where we worked with balancing equations and types of equations. So we're on to this.
We're going to get stuff we haven't done yet.
Yeah, we're going to get to some of the stuff that we haven't done yet. Okay, so basically be able to write equations, be able to translate those equations into particle view, be able to write a net ionic equation, an ionic equation, a molecular equation. Molecular equation is just a regular balanced equation. An ionic equation is everything that's soluble goes into its ions. A net ionic equation is where we cancel out things that are the same on both sides. I haven't had you write a total ionic equation. You just have got to realize you can be able to do that. Be able to do stoichiometry like our quiz today. Be able to relate volumes and figure out what is limiting, what am I going to run out of, what am I going to have too much of. Okay, be able to collect stuff on a decomposition or synthesis reaction. Then we get to this other side, use data from a synthesis or decomposition reaction to confirm this conservation of mass. Then we get to things that we have not covered yet. Some of it we have, but not all the way, so I didn't count it. We have talked about redox reactions here, but justify as far as in terms of electron transfer, we sort of did on learning objective 3.8, so you possibly could highlight that, but we haven't really done an experiment. Well, yes we have. We did the NEL. We did the NEL, so these two should be highlighted. So I'm going to put a little star right here, or try to, or not. Where did we go? Come on, come down. Now it won't let me go down. Whoa, hello. Okay, so it's not going to let me, but 3.8 and 3.9 we should have highlighted, and we should have highlighted 3.3b3. So we'll highlight those. I don't know why it's not letting me. There we go. There, let me. Okay. We haven't talked about energy moving. We have a little bit, but not a lot. Whoa. Down here at the bottom, electrochemistry, you should be able to draw a cell, be able to tell me what's going on with that cell, make me a qualitative and quantitative, in other words, tell me how much electricity is being made, analyze data from the cell to tell me what side is being reduced, what side is being oxidized, what's the anode, what's the cathode, that kind of fun stuff. We have not covered anything in 4, 5, or 6. So just make sure, yeah, no, 4, 5, or 6. So you are responsible for what we highlighted for the test. So what I'm going to have you do now is go to the blog, because you should have your computer up, and I want you to click on Learnerator, however you say that. Learnerator. Learnerator. Okay, this is a good site for you to go to because you can actually go through and try and see where you're at each of these. We have done big idea 1, 2, and most of 3. So for the test, you want to review 1, 2, and 3, and it gives you concepts within each of these, and you can see how well you're doing. So when you hit the test, you won't bomb, hopefully. So today and next time, we are going to be working on this. It's a bunch of little tests. So if I click in here, so Learnerator underneath the blog. Okay. Oh, you mean Learnerator? Yeah. What? Learnerator. Oh, it says Learnerator. Okay, whatever. Okay, so you go through and ask your question, you do your answer, you pick your answer, and you submit.
So do we all start with concept A?
I would
Let's do it.
do it. You want to write down where you finish, or actually I think it keeps track of it. We're going to work on this again next time, and then the next time is a semester test. We will do the written part first, and then we will do the multiple choice
We
after.
have the test on Monday.
So Tuesday.
Oh.
Tuesday and Thursday. No. Okay. Okay, so go through. It gives you some easy, then it gives you some moderate, then it gives you some difficult ones. You're going to go through and it'll tell you what you get for your answer, okay? So I'm not going to, if you want to pay more, you can get full access, but I think this is a good place to start, okay? If you need help, I can come around and help you.
I got a little check mark. Let me try to write music.
So are we turning this into our file today?
Yep, you're turning it into your file today. So gas laws should be coming in today.
We don't know if we get the same answer.
Finish it and get it in. Last time I'll accept any late work is Friday. Remember, if you need help, that gas loss thing is up here. So if you're stuck,
Right on my face.